This is the 19th and last video for the Artificial Intelligence course. And I'm now going to move on to talking about classical neural networks and how you train them using the backpropagation algorithm, which I'm going to derive. And the starting point here is that perceptrons, in their own right, aren't very powerful. And there are lots of problems they can't solve. And on the left here, I have the classical problem that perceptrons can't solve, called the Parity Problem. This is a classification problem with two classes. The little blue clusters are one class and the red clusters are the other. And for this problem we have two features, x1 and x2. So the idea of training a machine learning system to solve this problem involves coming up with a hypothesis that you can put x1 and x2 into, and which will output an indication of whether they belong to one class or the other. And because a perceptron is linear, and in this case we have one with a sigmoid activation function, it's not possible to divide these two classes using a perceptron because it will just attempt to draw a line between them, and clearly you cannot divide these classes using just a straight line. Now this was actually quite a major problem in neural network research for quite a long time, until the idea of using gradient descent, using differentiable activation functions came along. And the solution is to use machine learning systems that can compute functions that are more flexible and interesting than just linear ones. So how are we going to exploit what we know so far to compute more interesting functions? Well, we're essentially just going to connect a whole bunch of perceptrons together. So what I have illustrated here is the classical pictorial representation of a perceptron. We now have inputs to the perceptron, which I'm now going to denote using Z, rather than X, because I want to keep X for actual features, whereas these may not correspond to features in training data or data that we want to actually classify. The inputs are coming in, each one is multiplied by its corresponding weight. As previously, we have a special input that's always equal to 1, that gives us the bias weight W0. A node takes the products of the weights with the inputs and adds them up. That gives us something called the activation, and that's passed through the activation function, sigma, in order to give us an output also labelled Z, because it may well be used as an input to another perceptron. Now we're actually going to call these nodes, and if this is the jth node, then the output, the activation, is AJ, and the overall output after going through the activation function is ZJ. And because I'm continuing with the same kind of notation as previously, we can collect these inputs for some perceptron together into a vector Z, and we can collect the weights for that perceptron, or for that node, the jth node, together into a vector called W, and the summation that's performed by the node can then just be written as an inner product, W transpose Z. And with that in mind, we can form a multi-layer perceptron. And these are formed by just connecting a whole bunch of perceptrons, a whole bunch of nodes together, in a way that is only restricted in the sense that it doesn't have loops. So this is a directed acyclic graph with each node being a perceptron. And any feature vector that we have, with features x1 up to xn, provides inputs to some of the nodes, and their outputs are passed on to others, which are passed on to others potentially. And eventually we get a node that produces an output, and this is the output of the network. Now this does entail a slight change in notation, which is that W with the subscript I arrow j now denotes a weight going from node I to node j. So all that we've really done there is to generalize things a bit so that we're not just talking about one perceptron, we're talking about a whole bunch of them connected together. And because we've allowed outputs from some perceptrons to be inputs to others, we're actually computing something overall that's more interesting than just essentially linear. So that's what we're now using to compute a hypothesis. By setting weights within that network of perceptrons, we set the function that it computes and therefore the hypothesis that we're going to use to do classification. And now the problem is the same as before. If we've got a bunch of instances and each has a label, so we have a training sequence with m things in it, we can take the same approach again, define a measure of the error, which is a measure of the error that the network makes on the training set. This is a function of w, where importantly now, w is the vector of all the weights in the network, by which I mean the weights for all of the perceptrons, all of the nodes, all collected together into one big weight vector w. And we want to try and find a setting for those weights that minimizes E of w using gradient descent. And the process here is precisely the same as before. We want to find the partial derivative of E of w with respect to w. And to do that, we need to calculate the partial derivative of E of w with respect to every individual weight. And I'm going to make an important observation here, and I could have done this when deriving gradient descent for just a perceptron on its own, but there it makes kind of less sense in the big picture. E of w, our measure of error, is usually the sum of a bunch of components with one for each example. And we can certainly write the sum of the squared errors that way, because it's just the sum over each example of the squared error for that example. And that means that we can write it as E of w is equal to a sum over the examples going from 1 to m of some error term, E subscript p of w, which only applies to that individual example. And then because differentiation can be moved through the summation, we actually only need to calculate the derivative of an individual term of the error corresponding to a single example with respect to w. So to be explicit, what we've been using so far is an E of w that looks like the sum, and let's use the subscript p here because it's going to fit the notation on the slide, from 1 to m, okay, so over the individual things in the training set of yi, the label minus h, w and xi all squared. Okay, so E of w here is a sum of terms, and each term only involves one training example. So we can clearly write it like this, because this guy here is E P W. And then because we can take the derivative through the summation sign and get this, what we actually need to compute is just d of this by d weight from I to j for each weight in the network. Okay? So the key point is we're only dealing with one example at a time. And you will of course have noticed that I put in a deliberate error there. This and this should both be p. Now, there are some things which you will not understand the first time you see them, and this is one of them. It is entirely my expectation that you will have to work through this and the following few slides more than once, but please be assured that it looks far more complicated than it is, and remember all the time that all we are doing is computing a partial derivative. It's a partial derivative that may involve computing a function of a function in quite a lot of different places and then bringing all the pieces together. But ultimately, that is all we're doing. There's just quite a lot of it, and the notation is a little fierce. So start out expecting that you may have to follow this through a couple of times. The first step is just to place the pth example at the input to the network, and then calculate the resulting activations and node outputs, AJ and ZJ, for each node J, and continue that all the way through the network until you get a final output. This part of the process is called forward propagation. In short, get the pth example, put its feature vector on the input, and work out what the output Y is. That is the prediction that the network is making as to what it thinks YP should be, okay, the label in the training set for the pth example. Now once you've done that, the process of computing the derivatives that you need, which is called backpropagation, starts from the output node and works its way back to the inputs. And we can start by saying something that works in general throughout the network. And the observation here is that if we take the expression that we're fundamentally interested in, which is the derivative of the error for the pth example with respect to some weight going from the ith node to the jth node, then we can split it because we can consider the error term as a function of the weight from I to j as being a function of a function, because changing the weight from I to j will change the value of the activation aj, and the change in the activation aj will affect the error for the pth example. So we have a function of a function here, and we can split the quantity of interest into this product. Now the second of those terms, the derivative of the activation with respect to the weight, is easy. And it's easy regardless of which weight it is that we're interested in. And the reason for that is that if we write out the expression for the activation of the jth node in full, well, if you look back at the diagram, the pictorial representation of Perceptron, it should be clear that it's just a weighted sum. So we can write that out in full, which is what we have here. This derivative is just the derivative with respect to the weight from I to j of this sum, which is the expression for the activation of the jth node. It's the sum of the product of each weight going into the jth node with its corresponding input. And as we've already seen several times, if we write that out exhaustively, think of it like this. I've got a bunch of nodes k1 up to, well, ultimately up to kq, and one of those is actually node I, and those are connected to node j, which is producing an output, which is aj. Now, in order to keep the notation concise, I'm calling these inputs, in this case Z, input for K1, this one is input for I, this is input for K. The final one, the qth, of the things feeding into node J. So if I write this sum out in full, I get something that looks like the weight from K1 to J times the corresponding input, plus dot dot dot, plus at some point the weight from I to J is the corresponding input, plus dot 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 all the way up to weight from the qth thing to J times the corresponding input. Now, as has often previously been the case, when I differentiate this with respect to the weight from I to j, the only term that has that in it is this one, so all the others become 0, and my actual derivative then, well, if I differentiate w from I to j multiplied by zi, by W from I to J, I just end up with Zi. Okay, so that's easy. And that means that I can always write the thing that I'm interested in as a term delta J multiplied by Zi, which comes straight from here, where delta J is this expression. It's the derivative of our error for the pth example with respect to the activation of the jth node. Now what that means is that fundamentally the thing we need to concentrate on computing is the delta. This is what we want to know how to compute, because regardless of which node in the network it is that we're talking about, the other part of the expression of interest is just Zi, and that's easy. So now all that's left is to work out how to compute the values delta J for each node J in the network. And the fundamental idea is that we start out by doing this for the output node, and then we work backwards. And at any point, we can compute delta J for a node of interest using the values of delta J that we computed at the preceding step. So we need to start by working out what delta J would be for an output node. Well, in this case, the computation is pretty straightforward. We have Y being the output of the network, and that's the ultimate output of the very last perceptron. So in this case, J is an output node, and Zj, its ultimate output, is just Y, the prediction that we're making, and we're directly incorporating that into the measurement of error for the pth example. Delta J now is the derivative of the error for the pth example with respect to the activation of the jth node, in this case the output node. Now, in the current situation, you can look at it like this. The output node is producing an activation AJ, which is going through an activation function sigma, which is producing Zj, which is actually equal to Y, the ultimate output of the network. And to use the running example of the error being the squared difference between the prediction and the label in P, well, that's straightforward, because Y is our output and YP is just the label in the training set, and we're taking the difference squared. We'll come back to that in a moment. We want to know the derivative of the error with respect to the activation AJ, and now we can treat that as a function of a function, because changing the activation AJ changes the output Y, and changing the output Y changes the measure of error. Now, that means that we just split as a function of a function, as Y is in fact equal to sigma of AJ, okay, because that's also Zj. This derivative is just the derivative of whatever activation function it is that we're using, and that just leaves us with the derivative of the error for the pth example with respect to the output Y. And that's generally easy to compute as well, because we get to specify what the error is. So in the running example for squared errors, we're just interested in differentiating this, and that is entirely straightforward. So we can compute the delta value, delta J, for an output node, because it's just a straightforward term obtained by differentiating our measure of error multiplied by the derivative of the activation function that we have on the output. Now that's the case for an output node. But once we've got the delta for an output node, we then need to work backwards, computing delta values for nodes that come before the output. And this is a little bit more complicated. So what I have here is a representation of the fact that if we want to know delta J for this chap here, we're going to assume that we know what the delta is for all the nodes that it's connected to. Okay, for all the nodes that its output is connected to. That's the nodes on the right here. So we're going to assume that we know in this case the delta for node K1 and the delta for node K2 all the way up to the delta for node KQ. Okay, so we have Q nodes that are connected to the output of J, which is the thing that we want to know the delta for. Now the key observation is that delta is defined as the derivative of the error for the pth example with respect to the activation for the jth node. Now clearly, if the activation for the jth node changes, that can affect the output of the jth node here. That's connected to all the nodes K1, K2 up to KQ. In turn, that alteration to A sub j can affect all of the outputs for these nodes, and each of those can ultimately affect the error. So now we have a function of a function again, but we need the full chain rule. And the full chain rule was the second of the two questions that I gave you right at the beginning of the course to go back and take a look at, just to make sure that you understood how it worked. But the way to think about it is that ultimately EP, the error for the pth example, is a function of the outputs for all of these nodes, and each of those outputs is a function of AJ for this node. So we have a function of a function in order to compute the thing of interest, and we need the full version of the chain rule. Now if I write the full version of the chain rule out for the current setup, what I have is that our delta value of interest is this derivative, and that is in a sense a function of a function, and the full chain rule comes out looking like this. It's sum over all the things that the jth node is connected to, that's these guys here, of dEP by dAk. Now that's actually just the definition of delta for node K, and we're assuming that we know those because we computed them at an earlier stage in the process. Okay, so that is just delta for K, and then we have the derivative of the activation for each of these nodes that J is connected to with respect to the activation for J. Okay, so these guys are the derivatives of these values with respect to this guy. So now the only thing that's left is this term, because everything else is now known. Now the next slide really just sums that up. Because we know how to compute the delta values for the output node, we can work backwards, computing further delta values, which means that we know all the values delta k for the nodes ahead of where we are, and this is why it's called backpropagation. So now we're left with just one more thing left to do, and that's to compute derivatives like this, the derivative of the activation of a node with respect to the activation of a node that's connected to its input, So now we're twiddling a quantity like AJ, and we want to know something about its effect on one of these guys here. Well, let's say it's actually the first one we're interested in, because the same argument applies everywhere. If you look at the equation for AK, it looks like this. Once again, we have a summation, and it turns out that makes differentiating it very easily, because that summation is over each of the inputs that are coming into the node of interest. So it's a sum over this input plus this input all the way to this one. So these weights are coming from all the nodes connected to this, and these activations are the outputs of nodes that are coming from elsewhere. And notice that only one of those will actually depend on AJ, okay, namely this input. So when we differentiate that sum, all with the exception of one term will end up being 0, namely the term that is the weight from J to K times sigma for AJ. So this entire expression becomes d by dAj of the weight from J to K times sigma Aj. And differentiating that is easy. It's just W from J to K. And now we take the derivative of the activation function again. And hooray, these two things match, as we would expect. So now, if we put everything together, just looking back briefly at the last slide, but one, we had this expression that's summing a whole bunch of these together, okay, over all of the things that the jth node is connected to. We end up with the expression at the bottom of the slide. And we have an expression for delta J for a non-output node in terms of the delta values for all the nodes that it's connected to. And we have weights here, which we know about, and derivatives of the activation functions here that we know about. And with a slight rearrangement, we end up with the full expression. So this slide really just summarizes those steps. If you want to calculate the derivative of the error for the pth example with respect to all the weights in the network, this is the thing that we're going to all this trouble for. You apply the pth feature vector and calculate all the outputs for all the nodes until you get all the way to the output of the network. For the output node, we have quite a nice straightforward expression which tells us the derivative of the error for the pth example with respect to each of the weights going into the output node. And if you look back at the derivation earlier, you will see when you collect everything together you get this. And for non-input nodes, well, as we've just shown, the derivative with respect to the weight for node J has this expression, and we're calculating in terms of the deltas for the nodes that it's connected to. And that's the backpropagation algorithm. And it is extremely general. You can rework it with minor modifications for different kinds of measurement of error on the training set, and it's easy to incorporate different kinds of activation function into it because they only appear as the derivatives of the activation function. And with not a great deal of extra effort, you can modify it so that it works for nodes that do things other than just take a weighted sum. and so with this algorithm you can get quite a long way. Now, all it's doing is computing the derivative of the error with respect to the weights. After you've done that, you can use not just gradient descent, but any optimization method that operates on the basis of the gradient only. And there are numerous ways of improving on just straight gradient descent, which unfortunately I don't have time to talk about. But really the key central idea here is the computation of gradients, and that's what backpropagation is for. And I'm going to finish just with an example. For many, many years, until the availability of the necessary computational power became more common, pretty much the only kind of multilayer perceptron that you would see would be one which takes its inputs, applies all of them to a collection of what are called hidden nodes in a single layer, and then directs the outputs of those nodes to a single output node. So what does backpropagation look like in this case? Well, I'm going to derive it for an output node that just uses an entirely straightforward linear activation, and for which the hidden nodes all use the sigmoid activation. Now, the derivative of the linear activation function is straightforward because it's just 1. And for the hidden nodes, well, we can use one of the nice properties of the sigmoid activation function, which is that its derivative is expressed in terms of itself. If you have a quiet 10 minutes, you can verify that. And I'm going to keep using the same definition of error. It's the sum of the squares of the differences between the output and the desired output yp over all examples. And the error for the pth example is just exactly what you expect. It's just the term that corresponds to the pth example. Now, if you look at the general equations that we've just derived, then you can apply them in this specific case and work out what your expressions for the gradients are. So we saw that the general expression for the gradient for an output node looks like this, and the final term is straightforward because we know that we have quite a nice form for the error for the pth training example, and that's easy to differentiate in order to get this. And because the activation function on the output is linear, its derivative is 1, that tells us that the value of delta for the output node is straightforward. And so for the derivative, the only thing that needs adding to that is this term here, and we have the derivative that we need. And as we now have a delta value for the output node, we can compute delta for all the hidden nodes, and consequently we can get the derivative we want for all of the hidden nodes because we've already got the general expression. Now, there is only one output, so each of these hidden nodes is only connected to one thing, so there is no sum here. There's just the term for the output node. Now, looking through this general expression one bit at a time, given that there's only one element in the sum here, the z is carried straight over, we know what it is. The activation function is sigmoid, so its derivative is this part. And there's only one thing in the sum, which is delta for the output node times the weight from j to the output. Now we know delta for the output from the preceding step, so this guy is known, and collecting it all together we have a derivative for an arbitrary weight for any of the hidden nodes. Now, having obtained those derivatives, we can apply gradient descent. There is one extra nicety that we can add here, which is that using the version of gradient descent that I've shown you so far, we would actually do batch gradient descent What that means is that the actual derivative of the error with respect to all the weights is the sum of the derivative for the individual examples, and we would collect all those together and we would use those in our gradient descent. But it can be advantageous to actually do this update one pattern at a time. So each time you find the derivative for one example, you can immediately do an update with it using the derivative of the error for the pth example rather than the whole thing. And that's called sequential gradient descent. And as a final demonstration, and I'd like you to actually try coding and running a variation on this as one of the exercises in the problem sheet, we can make a little demonstration that a multi-layer perceptron now can solve the parity problem, which a single perceptron on its own couldn't. So I've applied this to a multi-layer perceptron with 2 inputs and 1 output. The hidden layer's got 5 units in it. The step that I'm using for the step size in gradient descent is 0.01, and all the other details are as in the example that we've just looked at. And I've just generated some noisy data for the parity problem, 40 examples, and done sequential gradient descent for 1,000 repetitions. And as we might hope, we end up with a solution for which the shaded area is where you predict that a new example would be in the red cluster, and the unshaded area is the area where you predict that an unseen example would be in a blue cluster. And just as a matter of illustration, what you have here shows the training data lifted to a height of 0.5, corresponding to the output of the network. And on the right, you can see the actual output of the network, and you can see how it divides the two classes by giving an output of greater than a half for one class and of less than a half for the other. And this is what happens to the error on the training set during training. You can see that there's an initial very steep fall, after which it comes down quite nicely, and it doesn't take us too long to learn to separate the examples in the training set. And I will leave things there. I hope that's all given you a decent introduction to essentially the core of the last 70 or so years worth of artificial intelligence research. There are many other things I would like to have talked about, but 12 lectures is really not a great deal of time. Next year in particular, if you're interested in looking further into machine learning, then I hope to see you in my course on machine learning and Bayesian inference. Thank you for your attention.